All right, folks, once again, I was unable to record yesterday's lecture, so I'm giving it another go to make sure you've got resources for understanding what we talked about in class. So in class, we began and spent most of our time on understanding how to combine group orbitals from, say, pyramidal methyl and or bent CH2 into the molecular orbitals for larger molecules. And we decided to go through a few examples, though later on we may just show you the results and talk about where the orbitals come from. So recall that our alphabet of group orbitals for CH3, pyramidal CH3, is this sigma CH3 that's based on 1 and 2s orbitals. The pi CH3s, two degenerate pi CH3s that are based on a p orbital on carbon and then the 1s orbitals on each of the hydrogens. In the case on the left, the lobe of the 2p, let's see, x orbital, and this is our coordinate system, I forgot. There we go. The yellow lobe of the 2px orbital overlaps with this 1s orbital on hydrogen, and this lobe of the 2px orbital overlaps with these two 1s orbitals on hydrogen. In contrast, the 2py orbital has a node in the xy plane, so it can't overlap with this hydrogen and must instead only overlap with these two, with the wave function sign relationships as shown. And then we have this sigma out orbital with one lobe pointing in the direction of the next atom to which the methyl group would be bonded. For bent CH2, we have a similar set of orbitals, a sigma CH2, only one pi CH2, a sigma out, and then the leftover 2py orbital. Now this orbital has a node in the xz plane, and for bent CH2, the two carbon-hydrogen bonds are in the xz plane, and so they can have no orbital density, no electron density on those atoms for this orbital. Okay, so let's talk about how we might combine the two, combine the individual group orbitals together to get molecular orbitals for a set of molecules. And in this discussion, I'm not going to redraw what these orbitals look like because we have them up here. But what we will do is, let's say here is the energy level of the sigma CH2. Let's say here is the energy level of the pi CH2. Let's say here is the energy level of the sigma out. And let's say this is the energy level of the 2py orbital. And of course, we're going to combine two bent CH2s together to get new molecular orbitals out. So let's just put these group orbitals here. We're going to mix the two CH2 orbitals together, and in doing so we're going to get two new orbitals out. We'll get an orbital that we call sigma plus sigma. Let's put the CH2s in there. And this will be lower in energy. This is the plus combination. This will be lower in energy than the two orbitals that we started with. And then there will be a sigma minus sigma that's going to be a little bit higher in energy than the bonding orbital is lower. So let's see. We went like, let's just conserve space. We went 1 unit down there. Let's go 2 units, or maybe 1.5 units up here. This will be the sigma CH2 minus sigma CH2. And these orbitals look exactly like you would expect. Let's draw them. So for the plus combination, we would simply have the two sigma CH2s lined up with each other in phase. And just so that you're aware, what we've drawn here is exactly the same. It means exactly the same thing as what I might draw here. In other words, a continuous lobe of electron density with no change in the wave function sign. In contrast, for the minus combination, what we would have would be a phase change in between the two nuclei. Now, you might ask, isn't this an antibonding orbital? And the answer is yes and no. It has a phase change in between the two carbon nuclei, and so in that sense, it is carbon-carbon antibonding, but it also has the same phase between carbons and hydrogens, and so it's carbon-hydrogen bonding. So it's not a fully bonding or antibonding orbital. It's someplace in the middle. And if you wanted, we could draw what this orbital really looks like. We would have one lobe of electron density here, another lobe of electron density there. Sort of this lovely butterfly-looking thing with a switch in the wave function sign in the middle. Okay, and if you want to, you can include dotted lines here as a reminder for where the molecular orbitals come from, though they're not necessary. All right. So let's now combine the pi CH2s together. As before, when we combine two pi CH2s together, we're going to have the pi CH2 plus pi CH2 combination. And then we also expect to have the minus combination here, pi CH2 minus pi CH2. And remembering what the pi CH2 orbital looks like, we can now draw the new molecular orbital. So the pi CH2 had the 2px orbital on carbon overlapping in phase with the 1s orbitals on hydrogen, with a phase change corresponding to the line between the two carbons. There's a phase change here. The plus combination would simply have the two pi CH2 orbitals overlapping with each other side by side. That's side by side or pi type overlap. Okay. And this is both CH bonding in sort of a sigma sense and carbon-carbon bonding in sort of a pi sense. The out-of-phase combination is going to look, and since we're doing this, I didn't do this in class, but you may or may not find it useful. This would look like a continuous lobe of electron density on this side and another lobe of electron density on that side with a phase change in the middle. All right. The out of phase combination, or the minus combination of the pi CH2 orbitals is going to be very similar, only I'll paste it, but oops, need a smaller eraser than that. It's going to look exactly the same, only there's going to be a phase change or a node in between the two carbon nuclei. Now, again, you may ask, isn't this an antibonding orbital? Well, yes and no. It's antibonding in the carbon-carbon bond sense, but it still has overlap with no change in wave function sign between the carbons and the hydrogens, and so it's still carbon-hydrogen bonding. If we were to draw what this orbital looked like, what we would see would be in the plane of the page orbital lobes like this. Covering the space between carbons and hydrogens. All right, and again, if you like, you can put the dotted lines to remember where the orbitals come from, though they're not strictly necessary, and they may make your drawing a little more confusing. Now, sigma out, remember, as we did before for ethylene, when you overlap two sigma out orbitals together, they overlap really well because the sigma out has this lobe that projects directly into the space between the two nuclei, unlike the sigma CH2. And so when you overlap two sigma outs together, you get a really stabilizing interaction. So that's enough to bring the sigma out plus sigma out combination down here even lower in energy than the pi CH2 minus pi CH2 combination. What does this orbital look like? Well, it looks exactly like you would expect. You've got a lobe of electron density between the two nuclei, and then you've got in-phase overlap between the carbons and the hydrogens in the back. So you have a strong carbon-carbon bonding interaction, and then you have still some carbon-hydrogen bonding interactions. If you were to draw what this looks like, if you were to do the MO calculations and draw what this looks like, it sort of looks like a TIE fighter from Star Wars, if you don't know. Okay, so then we mix the two py orbitals together. And when we do that, this is the 2py plus 2py combination. Traditionally, we call this the pi orbital in sophomore organic chemistry. If you were to draw this, you would simply see lobes above the plane of the page in phase, and then below the plane of the page also overlapping with each other in phase, but there's a change in wave function sign in the plane of the page. This is the typical pi bond, and if we were to sort of represent what that looks like, there would be a continuous lobe of electron density above the plane of the page and below the plane of the page with a node in the plane of the page. How many times can I say that? And then we would also need to draw the 2py minus 2py combination, and that's going to look like this. There will be a node in between the two carbon nuclei. There will be a phase change as you go from one carbon nucleus to the other, and a phase change in the plane of the page. We would have called this maybe in your sophomore class the pi star. Now that we've constructed those orbitals, and there's a couple of things we left out. We haven't included the minus combination of the sigma out. We haven't included sigma out minus sigma out because it's high enough in energy that it's not filled and we don't need to worry about it. So let's see, we have 12 valence electrons in ethylene. So let's fill the orbitals up with the available electrons. 2, 4, 6, 8, 10, 12. So the highest occupied orbital is the 2py plus 2py, the one that's associated with the double bond, or the pi bond. We would have called this the pi orbital. We'll call that highest occupied molecular orbital. If ethylene were going to react as a nucleophile, it would be these electrons in the pi orbital, or in the 2py plus 2py orbital, that would do the attacking. And then the lowest unoccupied orbital is the 2py minus 2py combination, or we would have called that the pi star. Now, if you want to see whether what we did agrees with the results of MO calculations, I can take you to an app called Spartan, where we can draw ethylene. There it is. I'm going to download data from the database for ethylene. These MO calculations have already been done. I will press that, and we can start to see what these orbitals look like. So we've got a low energy one that envelops the whole molecule. That looks a lot like our sigma plus sigma, sigma CH2 plus sigma CH2. The next higher one is the sigma CH2 minus sigma CH2 combination that we drew here. Next, you'll have the pi CH2 plus pi CH2. Looks like what we drew there. Now, next we would predict the sigma out plus sigma out combination, and that is indeed what is next. And what do you know? It looks like a TIE fighter. Okay, sorry. Then we would expect the next one to be the pi minus pi CH2 minus pi CH2 combination. So let's look at that. And indeed, that's what we see. And then HOMO is the pi bond, or the 2py plus 2py orbital. And LUMO is the pi star, or the 2py minus 2py orbital. So using these group orbitals and a little bit of intuition and some principles that we've discussed in QMOT, you can come to a conclusion as to what all of the bonding orbitals and what the LUMO of ethylene, what they all look like. And if you can do that, then you can predict a lot about the reactivity of this molecule. As I said, you would predict for ethylene that the most reactive electrons would be in this 2py plus 2py orbital. And that's why when you, for example, expose an alkene to a strong acid, the thing that happens is the pi electrons in that 2py plus 2py orbital attack the proton of the acid. Nucleophile attacks electrophile. All right, so we went through that in a lot of detail. Let's do the same thing, but let's do it for formaldehyde. Okay, and to do this, again, we're going to combine 2 pi bent CH2 we're going to combine our bent CH2 orbitals with orbitals from oxygen. Now, we won't need to consider any geometry for oxygen because it's simply a single atom. So the orbitals we will have available from oxygen will be the 2s orbital from oxygen, the 2px, the 2py, and the 2pz. And I'll copy our coordinate system so that we know which directions x, y, and z are. It doesn't really matter, though it will be helpful for our discussion to be consistent. So remember one of the principles from QMOT, which is that orbitals, atomic orbitals from more electronegative elements are lower in energy atomic orbitals from more electronegative elements are lower in energy than are atomic orbitals from less electronegative elements. So that means for the 2p, x, y, and z for oxygen, if this is the 2py for bent CH2, then we're going to expect the p orbitals from oxygen to be substantially lower in energy. So let's put them here. Say the 2px, the 2py, and the 2pz. Similarly, we expect the 2s orbital from oxygen to be lower in energy than the 2s orbital from carbon. It's not clear how much lower because the sigma CH, it's not clear how much lower the oxygen 2s orbital should be than the sigma CH2 orbital, because unlike the oxygen 2s orbital, the sigma CH2 orbital has bonding character. So I don't know how much lower to put it. Let's not put it very much lower. Let's just sort of put it here. All right, and this would be the 2s orbital from oxygen. So without even worrying what these look like, we would suspect that we have a plus combination of the 2s orbital on oxygen with the sigma CH2. We'll call this sigma CH2 plus 2s. And then we'll also have a minus combination, and the minus will be destabilized by just a little bit more than the plus one was stabilized. This is a sigma CH2 minus 2s. If the 2s orbital is lower in energy than the sigma CH2 orbital, we would expect the new plus combination to be biased towards oxygen, more on oxygen than on carbon, and we would expect the minus combination to be more on carbon than on oxygen. So here is the scaffolding of our molecule. I would expect there to be more orbital on oxygen than on carbon. If we drew this out, or if we looked at our MO calculations and drew it out how it actually looks, it might look something like this with a little bit more. It would maybe look somewhat fish-like, more on the oxygen than on the carbons. And then we would expect the out-of-phase combination, or the minus combination, to be more on the carbons than on the oxygen. And it's not important that you be able to know how much more, simply that you expect there to be a difference and you know in which direction it goes. So maybe a larger lobe here and a smaller lobe there. Okay. Now, the pi CH2, which I'll just redraw here, is in the plane of the page and looks like this. And in order for it to overlap with one of the p orbitals, which one would it overlap with? Our available orbitals are the 2px, the 2py, which is coming out of the page, and then the 2pz, which is going left and right. So we want side-by-side overlap with our pi CH2. So the best candidate for that is the 2px. All right, so we'll add those together. Again, there's a difference in energy, difference in overlap. So we expect the bonding orbital to be, or the plus combination, the lower energy combination, to be mostly on carbon, and the higher energy combination to be mostly on oxygen. So let's put the lower energy combination here. This would be pi CH2 plus 2px. And then we need to go a little bit above the 2px orbital. Maybe let's put it here. This would be the pi CH2 minus 2px. We expect this one to be mostly on carbon, or mostly on the CH2 group, and we expect this one to be mostly on oxygen. Okay, fair enough. Let's draw how that looks. We'll draw a slightly smaller lobe there. We would have side-by-side in-phase overlap. And if I were to draw what this actually looked like, it would probably be something like this, a larger lobe on the carbon tapering off towards the oxygen. You'll notice if you go back and look at the pi CH2 plus pi CH2 for ethylene, it looks almost exactly like this, only in this case our orbital is leaning towards the CH2 rather than the oxygen. Okay, and then let's draw the minus combination. And we expect that to look like this, mostly, as we said, larger orbital coefficient on the oxygen, a little bit less on the carbon, and we expect a phase change in between the two nuclei. And if we drew this the way it's sort of going to look in our MO calculations, what we would see is smaller lobes here and larger lobes on that oxygen. Oops. We need to show a change in wave function sign. And it may help us to draw the dotted lines. Okay. Notice this is going to put our pi CH2 minus 2px higher in energy than the pi CH2 minus pi CH2 was for ethylene, and that has to do with the fact that we're mixing the pi CH2 with a 2px orbital that's not involved in bonding. Okay, now let's think about which orbital we might mix the sigma out with. The sigma out looks like this, has a large lobe of electron density pointing away from the carbon into the space where it might bond with something, sort of left and right. And the orbital that matches with that is the 2pz orbital. And as before, we mix these together and we're going to get a lower energy combination. This is the sigma out plus 2pz. And then there will be a higher in energy minus combination, but that's going to be high enough in energy that it's not going to be occupied, and it won't even be the LUMO, so we won't worry about it. To draw that combination, I might do so like this. I would show a large lobe in between the two nuclei. Oops, I wanted some yellow there. A lobe on the back side of that carbon where the carbon overlaps with the CH2 groups, and then another lobe back here on the oxygen with phase changes or changes in wave function sign at the carbon nucleus and at the oxygen nucleus. I don't totally know whether to expect the 2pz orbital to be lower or higher in energy than the sigma out, so I won't worry at this stage about whether this is biased towards one or the other. Lastly, we need to consider overlap with the 2py orbital. Recall that that looks like this for bent CH2, and the orbital that would overlap side by side with that 2py orbital on CH2 is simply the 2py orbital on oxygen. So again, lower than where the 2py on oxygen is. We expect to have the 2py plus 2py combination. Because the oxygen 2py is lower in energy than the carbon CH2 2py, I expect this to be mostly on oxygen. And then higher in energy than the carbon 2py orbital, I'm going to have the 2py minus 2py combination, and I expect this to be mostly on carbon. So let's draw how that would look. Again, you can use, you can use dotted lines if you want to, only I'm not that good at it. I have to like turn sideways and twist the iPad. All right, let's draw what that 2py plus 2py combination would look like, mostly on oxygen. So that will look like this with a larger lobe on the oxygen. There would be sort of in phase overlap above the plane of the page and below the plane of the page. We would call this the carbon-oxygen pi orbital or carbon-oxygen pi bond previously. And again, to just demonstrate what that might actually look like if we did the calculation, we'd expect to see a larger lobe on the oxygen. We'd expect to see some bias towards the oxygen because the oxygen 2py is lower in energy than the carbon 2py. Similarly, for the LUMO, the out-of-phase combination, we expect to see more of the LUMO on the carbon and correspondingly less of the LUMO on the oxygen, or rather more of the minus combination on the carbon and less of the minus combination on the oxygen. We would have called this the carbon-oxygen pi star, perhaps, in a sophomore organic course. All right. Now that we have all of the orbitals mixed together, as with ethylene, we have 12 valence electrons. So now let's fill up the orbitals with the available electrons. 2, 4, 6, 8, 10, and 12. Okay. So let's look at what that tells us about the most reactive electrons in the molecule, and also about the lowest energy empty orbital. So the pi CH2 minus 2px combination is the HOMO, and the LUMO, the lowest unoccupied empty orbital, is the 2py minus 2py combination, or the pi star. Okay, those electrons in that high energy orbital, we said that that orbital is mostly on oxygen. So if you're looking at our Lewis structure of formaldehyde, the question I asked in class was, which electrons in this Lewis structure do you think occupy this molecular orbital? And the answer you guys said is this represents sort of a lone pair on oxygen, but with CH bonding character. Okay. The next highest electrons are in the carbon-oxygen pi bond, the 2py plus 2py combination. And then you have another set of electrons that are carbon-oxygen bonding and carbon-hydrogen bonding, but also look sort of like lone pair on oxygen. So we might call this one also lone pair on oxygen, but with major CO and CH sigma bonding character. So effectively, what MO theory tells us is that you have two different lone pairs on oxygen. You have one that's higher in energy, one that's lower in energy. And if you were going to have the formaldehyde react as a nucleophile, which electrons would do the attacking? And of course, the answer is the highest energy lone pair electrons, not the electrons in the pi bond. And so if you were to bring a strong acid into the presence of formaldehyde, rather than pointing your arrow from the pi bond to the acid like we did for ethylene, you would have the arrow go from a lone pair on oxygen to the hydrogen of the acid. You would protonate the oxygen first. Similarly, if you were going to have a nucleophile attack the carbonyl, it would do so by attacking the LUMO, which is mostly on the carbonyl carbon. So we would draw something like that. Okay. I mentioned in class, it's not important right now, but we'll talk about it later, that the geometric differences between these two sort of lone pair electrons on oxygen play an important role in protein folding. This one is typically involved in hydrogen bonding, and this one is involved in something called the N to pi star interaction, which we'll talk about another time. For fun, let's go ahead and compare the orbitals that we've drawn here with our QMOD approach with those that we're going to get from molecular orbital calculations. Here is the sigma CH2 plus 2s orbital on oxygen. You can see that it is mostly on oxygen, like we showed there. Here is the out-of-phase combination that is mostly on carbon, just like we showed here. Next, we would expect to see pi CH2 plus 2px and bias towards the carbon. And that is indeed what we see. Next is this sigma out plus 2pz orbital. So let's look for that, and that we see here, and we see there's this looks sort of like a leaning TIE fighter with a large lobe of electron density on the oxygen, and this would correspond to somewhat to a lone pair on oxygen. Next, we expect to see the 2py plus 2py orbital, which would correspond to the pi bond, and there it is. We'd expect to see some bias maybe towards the lower energy oxygen. The HOMO is the pi CH2 minus 2px orbital. So looking over here, there we go. That's what it looks like. And in this case, it's difficult to determine whether it's mostly on oxygen or mostly on carbon. These lobes to the left look bigger because they need to envelop both carbons and hydrogens. And then we expect the LUMO to be the carbon-oxygen pi star, and we expect that to be mostly on carbon, and indeed it is. So this QMOD approach is powerful because with these group orbitals, we can combine them together to get the answers that you get out of quantum mechanical calculations, and you can come pretty close to what the results are even without consulting a computer. And this kind of back of the envelope or on the sash of the fume hood type scribbling to figure and reasoning to think about the reactivity of organic molecules is really important. Now, in just the last little bit, I want to show you how what we've learned can explain some interesting observations. So ionization energy is the energy required to remove an electron from the highest occupied orbital of a molecule all the way to infinite distance. So for ethylene, that would correspond to moving an electron from the HOMO, the carbon-carbon pi bond, all the way up to infinite distance. In contrast, for propene, which has a methyl group, it's like we had replaced one of the hydrogens of ethylene with the methyl group. The ionization is lower. That means it takes less energy to get it to infinite distance, and the only way that would be true is if somehow the HOMO for propene were higher in energy than the HOMO for ethylene. Let's see if we can reason how that might be the case using group orbitals. So I'm going to draw over here the carbon-carbon, well, the 2py plus 2py combination for ethylene, 2py plus 2py. And then we're going to imagine mixing that with one of the available orbitals from pyramidal methyl. So let's look at our available orbitals and see whether any of them look like they might be able to overlap with the 2py. Let's go ahead and take this one because this one looks like it has electron density above and below the plane of the page with a node in the XZ plane. And I think if I compare that to my 2py plus 2py orbital from ethylene, it looks like I ought to be able to overlap that with the appropriate wave function sign. And let me just take a second and adjust the wave function sign like this. So you can see that if I combined these together, the pink lobe on the above and below the plane of the page for the CH3 pi orbital would overlap with the pink lobe above and below, above the plane of the page for the 2py plus 2py orbital. In other words, we're conceptually making orbitals for propene by combining groups for ethylene with groups for pyramidal methyl. And we're just taking one of those. There are many other orbitals that we could mix together, but specifically we're focusing in on the 2py plus 2py orbital, which was the pi bond, right? So we would, if we mix these together, we would have, let's see, this is the pi CH3. So we would have pi CH3 plus the 2py combination, and then we would have the minus combination up here, and this would be pi CH3 minus the 2py plus 2py. If I drew these, what would it look like? Well, this gets a little bit tricky. This is the in-phase combination. And then this would be the out-of-phase combination. All right. And when bringing together these two orbitals, they would both be full of electrons. So when you mix them together, you end up with the highest energy electrons that used to be the HOMO in ethylene that are now still the HOMO for 2-propene only, or for propene only, they are higher in energy. Remember that if you mix a filled orbital with an empty orbital, the highest combination, the minus combination, is empty, and the lower combination is filled, and that's a stabilizing interaction. When you mix two orbitals that are already filled, you get one pair of electrons that's lower in energy and another that's higher in energy. And so this kind of mixing, because of this methyl group, actually destabilizes the HOMO, raises it in energy, and you'd predict then that maybe propene would be more reactive. Now, I mentioned just at the very end of class that you have heard that more substituted alkenes, that is alkenes with more alkyl groups in place of hydrogens, are more stable. Based on what we've talked about here, it seems like we're going down a path where we see that they're less stable. And the answer is no. The pi electrons, or the HOMO, is a little bit less stable, but in the other combinations that we haven't talked about, there is greater stabilization by incorporating the methyl group, and therefore you get an overall stabilized molecule. Just to give you a sense for how that works out, I'm going to go back to Spartan. We're going to put a carbon here and another carbon there. We're going to download the orbitals for propene. And you see how the HOMO for propene comes from mixing the pi CH3 and the 2py plus 2py on the double bond together with the minus combination. So here's the 2py part, and then over here is the pi CH3 part, and there's a phase change in between the two. Okay, and with that, we will end.